Okay, let's continue our discussion of ecosystems, and let's focus on the movement of materials through these systems. So materials, specific nutrients move between the living and non-living components of the system in what are known as biogeochemical cycles. Now, all things do this, all materials, or all materials that living things use in particular, but we'll focus on just a few of them. Some move faster than others through the system, and some are found in different places in the system. But again, they all cycle between the living and the non-living parts of the system. And so, again, you can find a fair amount of certain things in the living component, and they can acquire those materials from the non-living component. Plants can acquire things from the soil and the atmosphere, for example. As they break down, those materials can get back into the soil. Sometimes these materials can get buried long-term in the earth, become part of the fossil storage, if you will. Coal, oil, peat is essentially organic material that's been buried and not fully decayed. We release some of these things by burning these fossil fuels, for example. They can be in the rocks, and so as things get buried in the sediment, they can become part of the rock material. The weathering and erosion processes can release them from these particular areas where they're being stored. Okay, so let's look at a few biogeochemical cycles, how they're important to living things, where we find them, and how they move around. So, of course, the hydrologic cycle, the movement of water, is very important. Lots of water in the surface, particularly in the oceans. It gets up in the atmosphere through the process of evaporation. Condensation, formation of clouds. When the moisture level, the water droplets in those clouds get too big, it comes out as precipitation, either over the ocean or over land. When the water hits the land, it can flow over the land, or it can flow into the land. If it flows into the land, it becomes part of the soil water or the groundwater. And essentially it flows ultimately back into bodies of water and then down rivers, etc., back to the ocean. And it's sunlight that drives this whole system, that causes the evaporation, that helps to form wind, that moves the clouds around, etc. Obviously important for living things. Carbon cycle. The carbon cycle is one where you find the element all over the place. You find a lot of it in the ground. We talked about those fossil fuels, also buried organic matter. Of course, a lot of it is in the living material, the living matter as well. We know carbon is the basis of organic compounds, organic molecules that make up the main backbone, the main component of living things. Through cellular respiration, release CO2 into the atmosphere. Photosynthesis takes it out. A significant way that humans impact the cycle is through the burning of fossil fuels, changing the levels of CO2 in the atmosphere. A fair amount of CO2 dissolved in the oceans. It's used to make compounds like bicarbonate. It's used in the making of the shells of organisms. When those things die, they can be buried and become part of the sediments, sort of long-term storage as well. Nitrogen cycle. The nitrogen cycle is what's known as a gaseous cycle because most of it is in the atmosphere as N2 gas. You perhaps are aware that the atmosphere consists of about 70% nitrogen gas. This relatively inert gas that we just breathe in and breathe out, we can't make use of it, even though we need nitrogen in our foods, in particular for making proteins. Now, fortunately, there are, though, bacteria that can do what's called nitrogen fixation. Hold on a second. Okay, back again now, nitrogen cycle. So again, there's these nitrogen-fixing bacteria. They can take N2 gas and convert it into ammonia, and then ammonium, and the also bacteria that convert it into nitrate and nitrite. And these forms of nitrogen can become available or are available in the soil for the plants, and then the plants can convert it into proteins that then can become available to the animals. Of course, when things decompose, their proteins can be broken down and made available as well. Now, of course, if this was just being taken out of the air, then the amount in the air would decrease, but we also have denitrifying bacteria that convert inorganic forms of nitrogen nitrate into nitrogen gas, thus completing the cycle. So we have bacteria that take it out of the air, these nitrogen-fixing bacteria, and bacteria that put it back into the air. And the living things make use of it along the way. Phosphorus cycle. Phosphorus cycle is known as a sedimentary cycle because most of the phosphorus is in the ground in rocks in the form of phosphate. Through the weathering of those rocks, the erosion of those rocks, it gets into aquatic systems and becomes available to plants. A relatively slow-moving cycle. Of course, when things die, they can become buried and it can be put back into the earth. But again, it's a very slow cycle of getting it out and making use of it. One way that people impact this cycle a lot is the mining of phosphate rocks and the creation of fertilizers from them. We sort of speed up the cycle. Okay, decomposers, of course, play a significant role in getting materials, say, back into the soil from the organisms that have died. Again, the rates at which things move and decompose varies a great deal. Decomposition rates are quite fast in the tropics, so things die and they don't stick around very long. They decompose quickly, where, of course, in temperate or Arctic areas, because of the shorter growing seasons, the processes will slow down. Okay, some experiments that have been done. So the plants in a community have a big impact on nutrient cycling. Places up in New Hampshire called Hubbard Brook, and there's been long-term experiments going on there that have added a lot to our knowledge of the movement of materials through systems. And what they've done is, so they have these mountainsides, these hillsides, and you've got these particular drainage basins here. And so there'll be a little stream running through each of these sort of little minor valleys, if you will. And so in this particular plot here, all the rainfall drains out through one particular stream. And so what they can do is they can set up these little dams and control the flow or monitor the flow of water out of that drainage basin and sample the water and see what's in the water. And so you can do that in an intact forest. And what they've done is manipulated some of the other drainage basins. So here they've clear-cut the trees from this one. And so what they saw was when they looked at the nitrate in the water, there would be these natural cycles where it would spike in the spring and then come down, and then the next year it would do the same thing. Well, what they saw is when they removed the vegetation from one of those drainage basins, the nitrogen levels then spiked. There was a significant loss, if you will, of nitrogen from the system in the one that had been cut. So that's not a good thing. They've done lots of other permutations of this, and again, each time they see that when they manipulate it, it really changes the nutrient dynamics in that system and sort of speeds up, most often, the loss of nutrients from that system. So once you clear cut that forest and try to grow it back, it's probably going to take longer than it would otherwise, or it's going to take a while for it to grow back and for those nutrient levels to build up because you've lost a lot of nitrogen from the system when you remove that vegetation. And again, we are impacting these systems in many ways. I mentioned the phosphorus cycle and the mining of phosphorus rocks. When we make these fertilizers that have nitrogen in them, phosphorus and potassium, other things, we impact these systems. So in our agricultural systems, we often have to add a lot of nutrients because we're trying to grow plants very intensively, and they're often plants like corn that can really take a lot of nutrients out of the soil, in particular nitrogen. So we have to supplement the soil by adding fertilizer in order to get the productivity levels we want. And so that, of course, makes for very fertile farmland and fields, but not all of that excess nitrogen is going to end up in the plants. Some of it is going to be washed out of the soil, and so what happens is it can cause, say, contamination of the groundwater. If you go a place like Iowa, you can't drink any of the groundwater there because there's too much nitrate in it. It's unhealthy levels because of all the nitrogen fertilizer they add. It can get off into the surface waters and cause eutrophication. Have you ever heard of dead zones, these hypoxic zones? What happens is, you can see here the Mississippi River drains a good chunk of the country, a lot of farmland, and so a lot of those excess nutrients are washing out of these rivers down the Mississippi and drain excuse me, at the Mississippi estuary where it meets the Gulf of Mexico. And so those excess nutrients cause these algal blooms. Those algae die, and then when they decompose, they suck a lot of the oxygen out of the water, and they form these dead zones, areas where there's little life because of a lack of oxygen. And these are found in many of the estuaries around the world, particularly ones where there's lots of agriculture occurring. Burning fossil fuels not only releases CO2 into the atmosphere, but also oxides of nitrogen and sulfur. And when these oxides of nitrogen and sulfur get into the air, they interact with water vapor to form sulfuric acid and nitric acid. Rainwater is naturally somewhat acidic because of the carbon dioxide in the atmosphere, which interacts with the water to form carbonic acid. But when you add these extra things, it can really lower the pH, and this can be damaging to vegetation that is downwind, in particular if you have a lot of coal-fired power plants, as we do here in the Midwest and the South. Downwind, you'll have some fairly acidic precipitation, which can have a negative impact on the forest. This is a problem in the Smokies, and particularly up in the Northeast. Excuse me. Now, there are ways to minimize that. You can have scrubbers on these power plants which can remove the oxides of nitrogen and sulfur, but it's expensive to do that, and the power companies are reluctant to do that unless they are told to do so. Again, you can see sometimes these pHs can get quite low. Also, if you release toxins into the environment, they can work their way up into the food chain in what's called biomagnification. And so the levels might not be all that high lower down in the food chain, but of course the zooplankton need a fair amount of the phytoplankton, and the small fish eat a fair amount of the zooplankton, and the bigger fish eat a fair amount of the smaller fish. And so what happens is the tissues, the concentrations of this material can get accumulated to higher and higher levels as you go further up the food chain, to where it can reach levels that can become detrimental to those animals. And so we saw this with DDT and the accumulating in eagles and compromising their ability to reproduce. PCBs, these compounds that used to be used in industry but are no longer used but are still in the systems. Again, this is known as biomagnification. Okay, well, I've got to stop and make a third video. We'll talk about CO2 and climate change.